All right, today we are going to start talking about types of mixtures and electrolytes. So we're going to get into start talking about solutions, which is the big section for this unit, and then primarily today we're going to talk about mixtures and electrolytes. Now, as a quick review, there are two types of mixtures. Okay, you have heterogeneous mixtures and you have homogeneous mixtures. Now, for heterogeneous mixtures, if you remember, these are mixtures where there are visible parts. Okay, way back in the year, we did an activity where we dropped a penny into water, and you could still see the penny in the water, so it was a visible a mixture that you could see each of the parts. Now, a mixture, if you remember, is something that can be physically separated. Okay, so, or separated by physical means. So things like just as simple as pulling something apart, um, all those things like decanting, vaporization, liquid chromatography, all those things that we can use. Now, homogeneous is when there are non-visible parts. And this was where we took some salt or some sodium chloride and we added it to water. Okay, once the salt dissolved, you couldn't see it anymore, but most of us know that if we leave salt water out, or we boil it down, we can get the salt back. So we can still separate it with physical means instead of having to undergo a chemical reaction. Okay, now some terminology, some vocabulary. There's lots of vocabulary in this unit again. If something is soluble, it's capable of being dissolved. The solid will gradually disappear as particles leave the crystal and mix with the water. You also, on the same token, have things that are insoluble or incapable of being dissolved. And then you also have a solution. All right, and for a solution, this is a homogeneous mixture of two or more substances, which we just kind of described earlier. Okay, so the particles cannot be seen. They're usually anywhere from 0.01 to 1 nanometer, which remember is pretty small because nano is times 10 to the ninth meters. So it's really, really, really small. Excuse me. Now, for parts of solutions, there's two terms that are really important. The solvent is what does the dissolving. Now, we have to have a broader definition and also include that this is the substance that has a larger volume, because a lot of times, if we come down here to seawater and sugar solution, this is where we think of, the water is the solvent. Excuse me. Then the other part of a solution is the solute. This is what is being dissolved, and this is what is the smaller volume. And again, if I come back down here to seawater, this is the ones we're most familiar with. We take a liquid, we dissolve something solid in sugar, salt, etc., etc. But what you can see from this table is that there are different types of solutions. For example, natural air, plain old room air, is a solution, but both the solute and the solutes, because there's really more than one, and the solvent is going to be gas. And typically in room air, nitrogen is what we refer to as the solvent because it just has the larger volume. It's the gas that's the most abundant. And then the solutes could be things like oxygen, carbon dioxide, water vapor, anything that's less concentrated than nitrogen. Okay, brass is the same thing. In brass, when the metals are melted down, you can add two metals together. And then they can be taken apart. Eventually, later, if you remelted them down and separated them by density or some other means. Carbonated water is the same thing. Instead of a solid dissolved in a liquid, or you have a gas dissolved in a liquid. So just different states of mixtures. Okay, now a suspension is a type of mixture with very large particles. Okay, very large particles. In fact, they're so large that they will essentially settle out if given the time, meaning that they will fall to the bottom. Okay, that they will fall to the bottom and have to be remixed. A really good example, and usually they're over 1,000 nanometers in diameter. And this can be separated using filtration. It's technically considered a heterogeneous mixture because you can see it pool down on the bottom. An example would be flour and water. Another example would be medications. Okay, if you ever get medications that are a suspension of a medication in liquid, for example, infant drops or liquid, medicines, it says shake vigorously before you use them because you have to get those large particles spread out again. Okay, so Just an example. Okay, colloids are medium-sized particles. They are 1 to 1,000 nanometers. So here we've got a little bit of Goldilocks and the Three Bears. We've got small, little, and just in the middle. It's in between a solution and a suspension. The particles do not settle, but they stay suspended. And these are kind of unique situations. They usually can appear cloudy or clear. The most common example is fog, where you have liquid particles of water dispersed in gas, which is the air. We've all seen that. Same thing with whipped cream. If you've ever had, whipped cream, when you the can that infuses the air to it, it's all it's doing. It's essentially forcing gas into a liquid and kind of dispersing it that way. Marshmallows are the same thing. Butter, cheese, those are all examples. We will not have to know colloid types. But we should be able to define a colloid and identify it as needed. Okay, now the way that you tell the difference between a colloid and a solution is what's called the Tyndall effect. Okay, so it differentiates, a fancy word for tell the difference between a solution and a colloid, since they both can appear clear. The beam of light is visible in a colloid, and light is reflected off of the particles because of their larger size. And we'll try this a little bit, but this is why you do not put your high beams on in fog, because literally in comes the light and you can see it kind of shines through, goes through this one, but then, and this is our solution where it simply passes right through. Then it hits the colloid and you can see it, but reality it kind of bounces back off. Okay, so this is why when you're driving with fog that, or you don't put your high beams on, because that light will be reflected right back in your eyes, and that's not so great if you've ever experienced that. So that's how we can tell the difference, and hopefully we'll get a chance to do that in class. Again, solutions versus colloids right here. It's just showing you the different sizes of particles and how things change. Okay, now electrolytes. There are 3 types of electrolytes. Now, electrolytes are strong, can be broken into strong based on strength. And strong electrolytes are substances that completely create ions in water, or in other words, those ions will dissociate or separate, or in simple versions, they'll uncrisscross themselves as from an ionic compound. Strong electrolytes conduct electricity because they have all these charged ion particles floating around. Weak ions will only partially separate or create ions in water, and they are partial conductors of electricity. And then you have non-electrolytes. This is our second kind of group of 3 where everything is related. These will not create ions in water, and they do not conduct electricity. So, for example, and I probably should have flip-flopped these slides, to define an electrolyte is a substance that dissolves in water that creates a solution that conducts electricity. Okay, or in other words, ions. So here's your definition of electrolytes. You've heard the term when it comes to Gatorade and other sports drinks and such, but then we define it as strong, medium, strong, weak, and non based on how many charged particles that they actually generate. There we go, by ability to dissolve. Excuse me. Strong electrolytes, these are examples. So you're going to want to add this up top here. These are examples of electrolytes. Strong electrolytes include what are called soluble ionic compounds. We're going to define that a little bit further, a little bit later. Also strong acids. There are 6 strong acids, and you need to write these down. And those are going to be hydrochloric acid, hydrobromic acid, hydriodic acid, nitric acid, sulfuric acid, which is H2SO4, and perchloric acid, which is HClO4. You have to know these. Okay, so write these down. Okay, there's probably, you have to know these 6, you just have to memorize them, because everything else that's not on this list is considered a weak acid, which falls it into the weak electrolyte standpoint. So weak electrolytes include water, weak acids, and weak bases, which we're going to get to acids and bases in the next unit. Non-electrolytes include all molecular compounds, so anything that is held together by a covalent bond only. And for example, sugar. Sugar is a long carbon chain. but it's all held together by covalent bonds. It doesn't form ions, so it's a non-electrolyte. And again, here you have no ions. Okay, this is methyl alcohol, and the light bulb does not go off. Here you have a solution of sodium chloride that's a whole bunch of charged particles, and the light shines very brightly to show you that it's a strong electrolyte. Here you have a solution where you have acetic acid, where some of them create ions, but a whole bunch of them don't. It's a weak acid, so it's a weak electrolyte, so it only partially conducts electricity. Okay, now how ions are made. There are two options, or two ways that ions, can be made. The first one is dissociation. Dissociation is when an ionic compound splits apart in water. Ionization is when a molecular compound creates ions in water. Okay, now for dissociation, an example of dissociation is sodium chloride. Remember, how do we know it's an ionic compound? Sodium chloride is a metal, chloride is a nonmetal. So when it splits apart, it forms sodium and chloride. Okay, so then you end up with the cation and the anion. And as soon as you have those ions that are separated, we know dissociation happened, and it's ionic compound. Ionization is when a molecular compound can create ions in water, and it only happens when the bond is weak, and it really almost always has to involve acids or bases. So it's not really common, but it is because hydrogen is so common throughout nature. But for example, hydrochloric acid can split apart to form the hydrogen ion and the chloride ion when it's dissolved, when it's in water. Okay, and then excuse me, you again have those ions floating around that make an electrolyte solution. Okay, now we do have to write what are called ionic equations. And essentially what happens is that this is just taking the ionic compound and splitting it into its ions. So for example, sodium phosphate, the first thing we have to do is write the formula for sodium phosphate. Sodium is a group 1 element. It's a 1 plus charge. Phosphate is PO4 with a 3 minus charge. So if I crisscross it and write the formula to start with, I would end up with Na3 PO4. Now when we just show it split into its ions, we just resplit it. We split it up back into sodium and phosphate. The only thing we have to take into consideration is we have to make sure it's balanced. So since we had a 3 there, we have to say that we formed 3 sodium ions. Okay, and that's again the whole reason why the ionic compound adds up to 0, because 3 plus signs, 1, 2, 3, can cancel out the 3 negative over here and get you equal to 0. Okay, now calcium nitrite, the calcium ion is a 2 plus, nitrite is an O2 with a 1 minus. So if I crisscross that one, I get Ca and O2, and I need 2 of them. So to write the ionic equation, I split it back up into the calcium ion, which is a 2 plus because it's a group 2, and 2 nitrite ions, which are NO2 with a 1 minus charge. Okay, now lastly we've got ammonium sulfate. Ammonium is a 1 plus. Sulfate, is SO, let's start over here, SO4 2 minus. I crisscross them, and this time I need 2 ammoniums and 1 sulfate. So then when it splits apart, I get 2 NH4 with a 1 plus, and I also end up with 1 sulfate. Now, just to show the signs here, to show you the chemistry that's going to take place, every situation we're talking about taking a solid, so you want to add the state in here for solid, and dissolving it in water. So when it's the ion, it's aqueous, but when it's still together in the solid form, it has the solid state. So you have to make sure you write S for the first 3 for solids, okay, because this is just like taking salt and dissolving in water, except we'd have a calcium nitrate solid or ammonium sulfate solid. We put it in water, and if they dissolve, then they are aqueous solutions. Okay, so we'll practice this, and then we'll get into some more things.